Edexcel Core Pure, Complex Numbers 4, de Moivre's theorem. De Moivre's theorem. Previously, you've been able to look at multiplying complex numbers together in polar form. If we write complex numbers in this modulus argument form, then we are able to multiply them together using the following rules. If we're looking at z1 times z2, then its modulus is the product of the modulus of z1 and z2. And if we are looking at the argument of z1 times z2, then it is the sum of the arguments of z1 and z2. So on the diagram, this product here, the red product z1, z2, the length of that red line is the length of the two blue lines multiplied together, and if we add the two angles together, the two arguments of z1 and z2, we get the argument of the answer. So that angle there, that big angle there, is the argument of z1 plus the argument of z2. So when we multiply complex numbers together, we see an enlargement effect and we see a rotation effect because we are adding the arguments together. And if we repeatedly multiply complex numbers together, we see a succession of enlargements and rotations. So if we now start to generalize our ideas and look at an expression for z to the n, we've defined z. This is our standard definition of z. Notice the plus sign in the middle of this modulus argument form, and it's cos theta plus I sine theta. Z squared can be defined as r squared cos 2 theta plus I sine 2 theta by applying de Moivre's theorem, and likewise we can define z cubed and z to the 4. Hence, we can start to think about generalizing this result, and it is extremely useful in mathematics, and particularly further mathematics, to realize that z to the n can be written as r to the n times cos n theta plus I sine n theta. This isn't, of course, a formal proof, but it is a generalized result that can be proved. So every time we multiply by another z, the power went up by 1 and the argument went up by an extra theta. So we went from r cubed to r to the 4, and the argument 3 theta became 4 theta. We're now going to look at a Geogebra file which looks at some of these features in a little bit more detail. So at the moment we're looking at the complex number z, which is the blue complex number, which at the moment is z equals 1 cos 0.44 radians plus I sine 0.44 radians, and we're looking at z squared. I've set n equal to 2, so the red one is z squared. Notice both of these lie on the unit circle because the magnitude of r is 1. So let's just keep the magnitude of r as 1 at the moment and just see what happens if we look at z squared and z cubed and z to the 4. So we've got z and z squared. Now we've got up to z to the 4, z to the 5, and every time I multiply by another z, you can see that we gain an extra angle theta as we go around. So the argument is going up by an extra theta each time. The modulus is still 1. Okay, so if you go back to z squared, the value of theta I've just left as a fairly small angle just to make things nice and clear. Let's see what happens when I make z a little bit longer. So I'm going to make its modulus, let's just go for 1.2. So the modulus of z is now 1.2, and I've left the argument at 0.44. You can see that z squared is clearly a little bit longer because the modulus of z is bigger than 1. And if you look at the angle, the argument for z squared, you can see it's theta plus another theta. And if I go to z cubed, you can see the modulus is getting bigger, and every time we multiply by another z, the argument goes up by an extra theta. And again, if I just go back to z squared, And let's see what happens if I make the modulus a little bit smaller than 1. So I'll just go for 0.95. So you can see the modulus of the original blue z is a little bit less than 1 now. And we can see z squared. So if I make n bigger, so we go to z, including z cubed, z to the 4, z to the 5, and you can see every time it gets a little bit shorter because we are doing a power of a complex number whose modulus is smaller than 1, but every time the argument goes up by an extra theta. So if I now leave it like that and just change r, so this is what happens when r is smaller than 1, and when r is 1, and when r is bigger than 1. We can see the effect. So if now we just consider the special case when the modulus of z is 1, in other words r equals 1, then we get this important result, that cos theta plus I sine theta to the power n can be written as cos n theta plus I sine n theta. And the important thing to notice here is the power n has generated n times the argument, the original argument theta. So the power n has been represented as cos n theta plus I sine n theta using de Moivre's theorem. The proof of de Moivre's theorem is in most textbooks and it's worth having a look at, but just to give you an idea, to prove the theorem for n is a positive integer, you would use an induction approach. To prove it for n equals 0, we can do that by observation. If you put n equals 0 into both sides of the theorem, you get 1 on this side, and on this side you get cos nothing is 1 plus I sine nothing, which would be 0. So z to the 0 does equal 1. And if you wanted to prove it for negative integer values of n, then you would start with n equals minus 1 and multiply by z. And again, these proofs can be found in most textbooks. In the next video, we're going to be looking at powers of complex numbers.